Next is the shortest route problem. In here we have a network. We have a starting point and an ending point connected through a network of nodes and arcs, and we want to determine what is the shortest route possible from the starting location to the ending location. So it'll be like you have a transportation network. You want to find what is the shortest path from one point A to point B. Okay, so here we have the plant, and these are the intermediate points, and then we have the warehouse. So each arc, the number that is associated with the arc is the distance. Now we want to know what is the shortest path from 1 to 6. So what we're going to do is we're going to set the supply at the plant to equal 1 and the demand for warehouse equal to 1, and all of these will be treated as transshipment point. So if that 1 comes in, that 1 has to go out, and then we just do a sum product of the flows with these distances, and that will give us the shortest route. So let's head on over to Excel. Okay, so here is the network. So let's first transfer all these numbers into a matrix from node the to node. Okay, so 1 to 2 is 100, 1 to 3 is 200, 2 to 3, okay, and this is a symmetric matrix. So 2 to 3 is 50 and 3 to 2 is 50. So 2 to 3, 3 to 2. Okay. Similarly 2 to 4, 4 to 2, 2 to 4. Okay. But for 1 and 6 you won't do the other way around, because from 1 the 1 is planned, so it's not a transshipment point. The supply of 1 can only go out, it cannot come back in, whereas in all the other nodes you can have like in 3 from 2 the flow can go from 2 to 3 or 3 to 2. So that's the reason why for all the transshipment points you have to code both direction of the arcs. Okay, let's format these. Okay. Now once again we have to enter all the origin and destinations. So origin from 1 you have 2 and 3. Okay, for 2 we have 3, 4 and 5. Okay, so for 2, so there is no 2 to 1. Okay, so you have only these 3, 2, 3, 4 and 5. And for 3 we have, okay, no 1, but 3 to 2, 3 to 5. And for 4 you have 4 to 2, 5 and 6. Then you have 5. Okay, 5 is 2, 3, 4 and 6. 4 and 6. 5, 2, 3, 4 and 6. Okay, next we have to set up origin and destination the other way around. Like if you can go from 1 to 2, you can also go, well, not 1 to 2, so you can, if you can go from 2 to 3, then you can also go from 3 to 2. So that must be set up. So which means, okay, the easiest way to do this is to take all the destinations, okay, and make them as origins. and make all the origins, okay, and make them as destinations. So that way both directions are covered, except that remember 1 and 6 have only one way. So you can have 1 as a destination or 6 as an origin. So here you have to come back here and then see these two ones must be removed. So ones are set up as destinations. So go and delete those 2 rows, and you can have 6 as an origin. So you have to delete that also. Okay. So now you have all the nodes set up correctly. So let's center this. All right. So now we can set up the distance as an index function. So we have index. All right. So that's the lookup table, and press F4, and then we have origin coming from here and destination coming from there. All right. So that's the distance. So here I missed this. 6 is in origin, so there are 2 nodes going, 2 edges going into 6. So since it was up here, I forgot about that. So we need to delete that as well. Okay. So now we have the distances, and these are the flows that we have to find. Okay. So now we have 6 nodes. I'm going to center that. And we need to set up net flow. Okay. So so we need some if. Okay. B19 to B42, make that absolute reference. So, and then comma this node. If this node is the origin, then you sum the flow. So this will be the amount of flow that is, again, press F4, will be going out. So when you use origin, so that would be flow that will be going out minus sum if, use destination. Okay. If the node is the destination, that is coming in. So press F4 and node 1, and then sum the flows. Okay. So here, yeah, node 1 cannot be a destination because it's not in the, we already deleted that. But I'm setting it up in this way so I can simply copy the same formula all the way through. So this is what is coming, what is going out minus what is coming in. So that's your net flow. So remember, we're going to have net flow equal to 1. So that 1, net flow equal to 1. Okay. So that net flow is equal to 1 for this node. For all other nodes up to 5, it must be 0, because that 1 flow, if it comes into the node, then it has to go out of the node. Okay. And for the last one, Okay, I'm copying the same formula. So this is the net flow. What is going out minus what is coming in. So for the last node, there is nothing going out. So one must come in. So this should be a minus 1. Okay. So one unit will traverse through this, and whichever edge that it traverses, the flow will be equal to 1. And then when you do when we do a sum product, then those edges, okay, here are the distances of all the edges, okay, in both directions, and then the flow will be equal to 1 for the selected edges. So this sum product will actually select the edges that are used and sum them. And so that would be the distance, and we want that distance to be the shortest. So we want to minimize that distance. We want to minimize that distance in such a way that there is one unit flowing out of node 1, and wherever else it goes, it flows out, and one unit comes in to 6. So that one unit, whichever edges that it is traveling through, okay, that sum should be minimum. So solver, all right. So our set objective is that one, and we want to minimize, and changing cell is the flow, right? And then, so since we have set this up as the same kind of net flow, then you can add the entire set of constraints in one batch. So that should be equal to that. So make sure that you select simplex ELP and make unconstrained variables non-negative. And here, okay, we don't have to worry about integer optimality because this is automatically integer, because there is only one unit going out and one unit traveling through, so it will be binary anyway. So just in case, I just made it into 0, but it's not necessary here. Okay, so here is the answer. So the path is the shortest path. So what is the shortest path? Okay, so here is a 1. So that is 1 to 2. Okay, and then that's a 1. So you go from 2 to 3. And the next one is here. All right, so well, we have to look at what happens from 3. So here is 3 to 5. And then you have 5 to 6. Okay, so that is the shortest path possible through. So 1 to 2, 2 to 3, 3 to 5, 5 to 6. So 190 to 90. That's your distance. And you're guaranteed that that is the shortest possible path from 1 to 6.